My name is Liana McFarlane Connolly,
And my name is Emily Aiken.
and we will be presenting our work on designing an aqueous hand warmer. Ionic compounds are made up of ions, or charged particles. When an ionic compound dissociates in water, its ions disperse and float freely through the water on their own. This dissociation comes with the release or absorption of energy in the form of heat, called the enthalpy of dissolution. If energy is released when the ionic compound is absorbed, it will cause a temperature rise in the surrounding water. We can harness this temperature rise for any number of applications. In this lab, we will attempt to create a hand warmer using the heat released by ionic compounds. However, since different substances release different amounts of heat, some will make for more efficient hand warmers than others.
Before we begin, it is important to understand the difference between absolute energy and temperature. A substance's heat of dissolution is measured in joules, which is a measure of total energy. However, when water is heated, its temperature increase is measured in degrees Celsius. This is a unit of average energy of the water's particles, created through kinetic movement. To convert from the joules released by the dissociation of an ionic solid to the resulting temperature change of water, we use water-specific heat. This is the amount of energy, in joules, needed to raise 1 gram of water by 1 degree Celsius. Water-specific heat is 4.18 joules per gram per degree Celsius.
The goal of this investigation was to design a hand warmer that raised 50 milliliters of water by 20 degrees Celsius in a short time, for a cheap price, and to analyze the results. We tested 7 ionic compounds: magnesium sulfate, sodium chloride, calcium chloride, sodium carbonate, sodium acetate, and ammonium nitrate to see which would make the most efficient hand warmer.
We decided that we wanted to pursue the most accurate temperature change, instead of finding the quickest reaction or the least costly reaction. Before beginning experimentation, we researched the heats of dissolution of the 7 ionic compounds. We found that magnesium sulfate and calcium chloride released the most energy, 91.2 kilojoules and 80 kilojoules respectively. Therefore, we expected magnesium sulfate and calcium chloride to be the most effective at raising the temperature of water.
We used a calorimeter consisting of an insulated styrofoam cup with a hole in the top for a thermometer to measure the enthalpies of dissolution for the ionic compounds. For each trial, we added a certain mass of water and a certain mass of ionic solid to the calorimeter. We then recorded the temperature change as the solid dissolved. The thermometer had a least count of 0.05 degrees and the mass scale had a least count of 0.0005.
We began our investigation with a series of preliminary trials to determine which ionic compounds had the highest experimental heats of dissolution. In these trials, we combined just 1 gram of each solid with only 30 milliliters of water, and recorded the resulting temperature change. After determining which ionic solids released the most energy, we performed 2 final trials, in which we combined over 10 grams of the most promising ionic solids with 50 milliliters of water, and recorded the resulting temperature changes.
Whenever energy was released into the water, however, the calorimeter itself absorbed some of it. Therefore, we had to calibrate our calorimeter by adding equal amounts of cold and hot water to the calorimeter and recording the final temperature. Knowing the mass and temperature of both water samples beforehand, we could calculate the heat released by the hot water and the heat absorbed by the cold water. The difference between the two would be the heat absorbed by the calorimeter.
Our preliminary trials revealed that 4 of the ionic compounds, magnesium sulfate, calcium chloride, sodium acetate, and ammonium nitrate, absorbed energy upon dissociation in water, and therefore would not be appropriate for use in a hand warmer. The remaining 3 ionic compounds, calcium chloride, sodium chloride, and lithium chloride, all released energy and raised the water's temperature. Therefore, we decided to use combinations of these 3 compounds in our final trials.
When we combined about 7.5 grams of calcium chloride and 5.5 grams of lithium chloride, it raised the temperature of 50 milliliters of water by 21 degrees Celsius in 41 seconds. This combination cost 48 cents. When we combined about a half a gram of calcium chloride, about 2 grams of lithium chloride, and about 9 grams of sodium carbonate, it only raised the water's temperature by 13.5 degrees in 50 seconds. However, this combination had the advantage of being cheaper, at only 26 cents.
Before calling our results final, however, we had to factor in the heat loss due to our calorimeter. We calculated that in making a 1 degree temperature change, 206.6 joules of energy were absorbed. We then calculated the heat loss to the calorimeter in our 21 degree temperature change, and added it to 21 degrees to find that, in reality, our combination of lithium chloride and calcium chloride released enough heat to raise 50 milliliters of water by 42.0 degrees Celsius.
The class data did not demonstrate many definite trends between cost, temperature change, and time. However, it did show a slight positive correlation between the cost of a combination of ionic solids and the temperature change it produced, as shown in this graph.
As shown here, there was no correlation between the cost of a combination and the time required for the heat change produced.
Our results disproved our hypothesis. We had suggested that magnesium sulfate and calcium chloride would cause the greatest rise in the water's temperature because they had the highest accepted heats of dissolution. However, magnesium sulfate did not raise the water's temperature. In fact, it lowered the temperature slightly. Instead, the ideal combination of ionic solids for heating was lithium chloride and calcium chloride, which raised the water's temperature to 21.6 degrees Celsius. This combination also takes only 41 seconds to cause the heat change and costs only 48 cents. This class data demonstrated that, while more expensive combinations of compounds did produce slightly greater temperature change, there was little correlation between the price of a hand warmer and its effectiveness.
The data we obtained was inaccurate with respect to temperature change, but accurate with respect to time. The class dataset was also not very accurate, with a high average error for both temperature change and time elapsed. Additionally, the class data was imprecise as it had an extremely wide spread and a high standard deviation. However, no outliers can be eliminated with respect to either temperature change or time elapsed.
Two main sources of error could have contributed to the lack of accuracy in both our individual results and the class results. First, it is possible that the ionic solids did not completely dissolve and dissociate in the water. This error was evidenced by the observation that some ionic solids were stuck to the sides of the calorimeter and the thermometer after the dissolution had taken place. This would lead to less heat being released and a smaller measured temperature change. Second, calcium chloride is a deliquescent anhydrous salt. Therefore, it is likely that while we were measuring and preparing our trial, the calcium chloride had already started to absorb water from the air and dissolve. This would result in a smaller measured temperature change.
Additional research could be done to further explore the options for a hand warmer. For example, ionic compounds could be dissolved in a liquid other than water. If this liquid's specific heat is less than that of water, its temperature will be raised further than water's by the dissolution of the same ionic solid. For example, ethanol has a specific heat of 2.44 joules per gram per degree Celsius, which is quite a bit less than water's specific heat of 4.18 joules per gram per degree Celsius. Therefore, the dissolution of an ionic compound in ethanol would make for a more efficient hand warmer than the dissolution of an ionic compound in water. Additional research could also determine what causes some ionic compounds to release heat when they dissolve while others absorb heat. Tests of the heat dissolution of many ionic compounds could reveal a pattern as to which release heat and which absorb it. Finally, one could adopt a method of experimentation similar to the one we used in this lab to design a hand cooler.
Thank you for listening.